Welcome to Homework Lib.
Hi, so for this question, it may seem that you need to do a very complicated calculation in order to get the concentrations of all of the species. But in analytical chemistry, what we're going to have is that whenever we are 2 units of pH below of the pKa for a species, we already know that we're going to have a 99.9% of the acidic version of that species present in solution. So what we can do is calculate the pKa's for the different Ka's that we have. So Ka1, that is 1 times 10 to the minus 7, which corresponds to a pKa equal to 7, right? And we have a Ka2, that is 1.3 times 10 to the minus 13, which corresponds to a pKa2 of 12.886. So we have these different Ka's, and we know that we have a solution of zero point 0.3 molar concentration of HCl. Remember, HCl is a strong acid, so it dissociates completely, and it corresponds to having a concentration of H3O plus equal to zero point 0.3 molar. Thus, the pH for our solution it is going to be equal to 0.523. Now, let's compare this pH with different pKa's. Let's do a scale of pH. We are here at 0.523. Then we have over here the 7. And over here, we're going to have the 12.886. And the species that are going to be present in each of the different equilibriums, over here, we're going to have H2S. Here, we're going to have HS minus, and over here we would have S2 minus. So just by looking at the pH that we have of our solution, let me make this 5 like more clear, we know that the only possible equilibrium that we need to consider is the one of H2S and HS minus. The other species it is not going to really contribute to what is present in solution. So we are what 12 units of pH away, so that is too much small value to be quantifiable in any possible case. So now with this we can proceed with our regularized table. We have H2S that when we have it in water, it is going to produce H3O plus plus HS minus. We can go ahead with our ice table. The initial concentration is going to be 0.1 molar. Of H3O plus, we are going to have an initial concentration of 0.3 molar. The amount of change, let's call it X. We're going to add plus X and plus X of these sides. And at the equilibrium, we're going to get 0.1 minus X, 0.3 plus X, and X. Now, this corresponds to the equation for Ka1, that is concentration of H3O plus times the concentration of HS minus divided by concentration of H2S. Here, the result it is going to be after replacing 0.3 plus x, x, and 0.1 minus x. And what this needs to be equal to the value for k, that is 1 times 10 to the minus 7. Now, over here we have two different options. Solve the full quadratic expression coming from this equation, generate the quadratic expression equally to 0 and find x1 and x2. And the other option that we have is making the approximation that 0.1 it is going to be much larger than x. If that is true, 0.3 plus x is going to be equal to 0.3, or approximately 0.3, and 0.1 minus x is going to be approximately 0.1. So my expression now becomes 1 times 10 to the minus 7 will be equal to 0.3 divided by 0.1 times x. Oops, wrong sign. Times x. 0.3 divided by 0.1, this is 3. So this implies that x is 1 times 10 to the minus 7 divided by 3, giving us 3.33 times 10 to the minus 8 molar. What is that x value? Well, that x value is the corresponding result for HS minus. So concentration of HS minus will be 3.33 times 10 to the minus 8. We also know that the concentration of HS, it is going to be 0.1 minus the value that I got. So this would be 0.099999966 if we want to be like super precise about it. But as you can see, we are mainly going to have H2S present in solution, something very close to 0.1. Now, for me and for most professors, this would be enough because the next equilibrium, we shouldn't consider it. It makes no sense because the value that you're going to get is going to be even smaller. But let's just get fun with it and get the concentration of S2 minus just for making clear why this approximation is more than good enough for this type of results. So what we are going to assume is the next equilibrium, H is minus plus water, is going to generate H2O plus S2 minus. And we're going to do our ice table again. In this case, I'm going to write it down as C0. This C0 is going to be this concentration that I have, because otherwise I would have to put that value again and again and again. Just correction here, this is in molar. And the value for H3O plus, we're going to have 0.3 plus X, right? So this is essentially just having 0.3, a bunch of zeros, and another 33, right? So 1, 2, 3, 4, 5, 6 zeros, 33. If you want to be like super thorough about it. So now the amount of change, it is going to be the same. This is going to be minus X. Over here we are going to add X, and of S2 minus we're going to have X at equilibrium C0 minus X plus 0.3, 4, 5, 6, 33, and X. That means that our Ka2 is equal to concentration of H3O plus times concentration of S2 minus divided by concentration of HS minus. Replacing the values again, I'm going to just put it as 0.3. It makes no sense numerically to include all of those zeros. It is not going to affect the result at all. And we know that X is going to be even smaller in this case, right? So I can go directly and use the same approximation that these two quantities, this is going to be essentially C0, and this is going to be essentially 0.3. Well, okay. So we get 3,000,000,000,033 divided by my value for C0 and times X. So the quantity X is going to be, just for you to see that everything matches up, the value for Ka, that is 1.3 times 10 to the minus 13, times the value for C0. What is that concentration? 3.33 times 10 to the minus 8. So we are already in the ranges of times 10 to the minus 21 divided by 0.3. Well, 3, 4, 5, 6, 33. Okay. So the result that we get is 1.443 times 10 to the minus 20 molar. As you can see, that is a value that you're not going to be able to detect anywhere, and this is going to be equal to the concentration of S2 minus. So, doing a little recap, essentially the only two possible species that you're going to have are H2S and HS minus. S2 minus, it makes no sense to do the calculations, but we did it anyways. The concentration for HS minus is 3.33 times 10 to the minus 8. The concentration of HS is going to be 0.1 minus this value, so this number that we got over here. And finally, the concentration of S2 minus, assuming those initial concentrations, would be the one that we got here, 1.443 times 10 to the minus 20 molar, which, as you can see, it's a value that is so small that it makes no sense to do the calculation. And that will be all. Thank you very much.